In this film, we take a look at how to optimize a function, that is, to find its largest and smallest value using the mean value theorem. So first of all, we take an example. So fx equals x to the third minus 3x plus 1. And this function I choose so that I have something that's fairly easy to differentiate. And well, so the question is, what are largest and smallest values? And you can also say, where are they taken? So for which x do they happen? So the main thing now is to compute the derivative and to use information on the derivative. So the derivative here looks like this. And the important thing now is to get the derivative on a factorized form. Well, this would be one factorized form, you could say, or we can factor even more and have it look like this. Now, using the derivative, or based on the derivative, we can make a table of signs. So here I do the real line, and then I write up all the factors here. So I don't care about the 3, so he doesn't affect whether or not he's positive. But these two guys do. So let me write each factor here. Now this guy, I mean, he's a straight line, and he crosses the x-axis at x is equal to 1, and he's negative to the left of this point, 0 at that point, then he's positive. Similarly, this guy here crosses at x minus 1, so here is negative, here is 0, and then it's positive everywhere here. So I'm just writing as many minuses and pluses as I can. Now if I multiply these two together with the factor 3, I get f prime. And f prime, well, here is minus times minus, so he's plus. Here is something finite times 0, so it's 0. And here is negative, 0, and positive. So what I'm doing here is I'm visualizing how to split the next step of this argument into cases. So I could do this in words as well, or use more fancy notation, but I won't get more information than what I'm seeing here, and this is actually a very nice way of visualizing it. And now I use the mean value theorem to pass from information on f prime to f. And to do this, I use the corollary of the mean value theorem, which says that if f derivative is positive on some interval I, this means f increasing on I. And similarly, if the derivative is negative on some interval I, then f is decreasing on I. And here I should say strictly decreasing, and here I should say strictly increasing. So here, where the derivative is positive, my function is strictly increasing. Here, where my derivative is negative, it's decreasing, and here it's increasing again. And now I see the largest and smallest values. And here, of course, I forgot. So to make things interesting, let's put the domain of this guy here to be the interval minus 2 to 3. So this makes it a little bit more interesting. It means I'm cutting off here at minus 2, and I'm cutting off here at 3. So what you can see now is that my graph is going up, down, up. It's starting here. So this is a candidate for a smallest value. This is a candidate for a largest value. This is a candidate for a smallest value. And this is a candidate for a largest value. And this guy here, he's called a local minimum point. This is called a local minimum. So the x value here is the local minimum point, and the corresponding y value would be the local minimum value. Similarly, here we have a local maximum, and here we have a local maximum. Why do I say local? I say local because when we look at x close to here, this will be the smallest value. If I look at x close to here, this will be the largest value. If I look at x close to here, this will be the smallest value, and similarly here. So to figure out what's the absolutely largest value and the absolutely smallest value, we need to compute the value of f at these points. So let's do a table here. So we have various candidates now. And notice when I've done my crude sketch of the function like this, I know that these are the only candidates for where I can take my largest and smallest values. There can be no other. So we plug them in. The candidates are minus 2, minus 1, 1, and 3. So I plug them in. So minus 2, I get minus 8 plus 6 plus 1, that's minus 1. Here I get minus 1 to the third, that's minus 1, plus 3 plus 1, that's 3. 1 minus 3 plus 1, that's still minus 1. And then I get, when I plug in the 3, I get 27 minus 9, that's 18 plus 1, that's 19. So here I get the value 19, here I get minus 1, here I get the value 3, and here I get the value minus 1. So I see that this here is the absolutely largest value I take. So we call him an absolute max. So this is a local maximum. That's also an absolute maximum. This is a local maximum. That's not an absolute maximum. This thing here, well, we have -1 at both these points. So this is a local minimum. That's also an absolute minimum. This local minimum here is also an absolute minimum. Okay, so you can have more than one absolute minimum point, but you have only one absolute minimum value. Some people also call this the global max and this the global minimum. But our conclusion is that this is the largest our function can be, and it happens at that point, and this thing here is the smallest our function can get, and it happens at those 2 points. And then we're done. Now, if we want to verify all of this, we can try to plot the graph. So let's do that. So let's see, we do x to the third minus 3x plus 1. Let's plot them from -2 to 3. And then we see. So here at -2, we're at -1. Well, it's not so clear, but we kind of know it. And here at -1, we're at -1. And here we're at 3. And here we're at 19. So of course, this sketch here is cruder than this one. But more or less, if we only care about finding the biggest and smallest values of f, this gives us all the relevant information.